Okay, good morning, good afternoon, and good night to everybody, everywhere. Today, I will discuss an important problem of and workout example of sensitivity analysis, how to solve the sensitivity analysis problem by simplex method. So, this sensitivity analysis, we will discuss the variation of cost vectors and requirement vectors. Now we'll try to solve this problem, solve the following linear programming problem and find the ranges of second cost vector and third cost vector and third requirement vector such that the optimum basis remain unchanged. The objective function is maximum z equals to twice x1 minus x2 plus thrice x3, and subject to the constant there are three constants, and 3x1 plus x2 minus twice x3 less equal to 6, twice x1 plus 5x2 plus x3 less equal to 14, twice x1 plus 4x2 plus twice x3 less equal to 8. And these three constants uh, has three decision variables x1, x2, x3, and this is the non-negativity restrictions. So here first c1 equals to 2, here positive cost vector, and here negative -1 is the c2, and c3 is the actually 3, third cost vector. So we'll discuss the discrete changes of this cost vector, that means c2 and c3, and the requirement vector 6, 14, 8. That means the we required vector b3 means 8, b1 equals to 6, b2 equals to 14, and b3 equals to 8. We'll discuss the discrete changes of this. Now we'll make a table with the coefficient of x1, x2, x3, and the constraints. Now introducing slack variables as three slack variable s1, s2, s3, which must be non-negatives to each inequality constants, and convert them to the equality equations like this. Just first constant plus s1 equals to 6, second constant plus s2, second slack variable equals to 14, and third constants plus third slack variable equals to 8. So there are decision variables, six decision variables x1, x2, x3, s1, s2, s3, and they must be actually non-negative. So there are six decision variable and three slack variable, and two is the our given decision variable, and this is the basic variable x1, x2, x3, and s1, s2, s3. The six variable must be non-negative. Also the objective function can be written as this is the given objective function plus 0 into s1 plus 0 into s2 plus 0 into s3. This is the new objective function. Now we'll make the table by using the coefficients of the constants and objective function. This is the first x1, x2, x3, s1, s2, s3. This is the coefficient of first constants, and this is the coefficient of second constants, and this is the coefficient of third constants. Okay, now we'll make the basic variable s1, s2, s3 considering, and x1, x2, x3 are non-basic. So here x3 in the z, this is the z values from the objective function. This is the coefficient of x1 and coefficient of x2 and coefficient of x3 from the objective function. This is the objective function 2, -1, 3. Okay, 0, 0, 0. So we get 2, -1, 3. Now we will observe from the z coefficient of objective function which will be the maximum. Actually 3 is the maximum, so x3 is the leading variable here. So by ratio test we can determine determine the pivotal element in the column of x3. This is the x3 column. Now this is the, since 3 is the maximum in this row, this is why this column will be the pivotal column. Therefore by ratio test means actually minimum of suppose in the second row, in the 14, this is the requirement vector 14, and so 14 by 1. Okay, and 6 by -2 cannot be accepted because this is the negative values. So 14 by 1, this is the minimum is 14, and 8 by 2. 8 by 2 means 4. So which is the minimum here? Actually 4. That means this third value is the actually pivotal element. So this we get the minimum value for this value 2. This is why this value is called pivotal element. Now therefore S3 leaves the basic. So S3 will leaves the basic and X3 will enter the basic. So S3 is the departing variable and X3 is the entering variable. So from the next table we get this one. That means X3. So and this will become S3. Now uh, so therefore and leading variable so the departing variable S3. Now we'll make the pivotal element unity. Okay, now reduce the pivotal element to unity and all other elements of the pivotal column will be 0 in the following table 2. So just dividing by 2 this third row, that means we'll get the third row or third row divided by 2. Just dividing by 2 we get this. And S3 is the departing variable, X3 is the entering variable here. This is the departing. So just reducing the pivotal element to unity and all other elements pivotal column to 0. That means 2 become 1 by dividing by 2 the whole 1. And now how we get this 0? Actually if we add twice the element of R3 with R1 we get the row 1. Okay, similarly row 2 how we'll get? Reduced row will be the second row plus third row from the previous one, second row plus third one. That means just adding twice, 2 multiply adding, and this just what? 3 thrice will be subtracting. So R2 plus R3 will be given by second row, and second row we will get this is the this becomes 0 just if we take the minus here. This is the actually minus the R2 minus R3. So similarly fourth row will be reduced fourth row equals to fourth row minus 3 into third row. We get this one. So again we observe the Z values. Z values here half and minus 7, only positive on this, and this is the maximum one. So X1 will be the leading variable here. So by ratio test we will determine the pivotal element in the column X1. Now we'll determine pivotal element by ratio test. Ratio test means what? Just requirement vector divided by the element of X1. 14 by 4 and 10 by 3 by 2 and 4 by half. So minimum will be what? 7 by 2. And we get the 7 by 2 in the first element. Okay, 14 by 4 divided by equal to 7 by 2. This is the actual minimum. So the pivotal element is 4. Therefore S1 leaving the basic, that means departing the variable, and X1 entering the basic variable. So similar process we get the table 4, just making unity, dividing by 4 in the first row we get unit element, and make other element to the 0. That means reduce pivotal element to unity and all other elements of pivotal column to 0 in the following table. So similar process we get the table. Just making 0. How we get make 0? The reduced second row reduced how? Second row plus third row. Okay, second row plus third row, second row plus third row, make the 0. So again, I'm repeating from table 2. Actually, this is the leading variable and become this is the pivotal element, and we have made this pivotal element unity 1 by dividing by 2 the whole R3. Okay, this was the row 3, and dividing by 2 we get 1 by 2, 4 by 2, 0 by 2, 0 by 2, 1 by 2, 8 by 2, that means 4. So we get this value. Now we will reduce the pivotal element to unity and all other elements of the pivotal column to 0. That means 3 becomes 0 and 1 becomes 0, minus 2 becomes 0. So how it will be happened in the next table? So in the next table, if we make this 0, how actually first row can be this 0 becomes r1 plus twice r3. Okay, twice r3, and second row becomes 0, r2 minus r3. Okay, and fourth row, this will be 0, fourth row minus 3 into row 3. So this way we get the reduced pivotal element column. Again, here this is the half is the actually most positive in the z values. This is the actually cj minus zj. So this is the leading variable. So by ratio test we determine the pivotal element in the column of x1. Now we get the minimum ratio 14 by 4, 10 by 3 by 2, 4 by half. So we get the minimum actually 7 by 2. 7 by 2 means what? 14 by 4. So 4 is the actually pivotal element. Therefore s1 leave the basic and x1 enter the basic. So in this way we get the, we making the unity 1, that means dividing by 4 the first row, dividing by 4 in the first row. So making reduce the pivotal element to unity and all other element to 0. So how we get this 0? Actually row 3 minus 3 by 2 into row 1, that we get 0, and half minus row 3 minus half row 1, we get this 0. Similarly we get row 4. So in this just reducing in this way, we get the pivotal element 0 and pivotal column 0 and pivotal element 2 unit. So hence the optimality conditions are satisfied and the optimum solutions are x1 equals to what? This is the x1 and this value will be the requirement vector 7 by 2. Here x2 is not basic, this is why 0, and x3 is the basic. Basic means what? 9 by 4. So maximum z equals to, actually we get 55 by 4. So by simplex method, we have actually obtain the optimal solution of the given linear programming problem. So this is the actually solution 7 by 2, x1, and x3 is the 9 by 4. But s2 can does not affect the solution because it has 0 coefficient. 0 into s2, this is why 19 by 4 cannot be accepted. So the optimal solution is this, and maximum z will be 55 by 4. Now we will discuss the actually sensitivity analysis for the second cost vector and third cost vector. Now since second cost vector is not to the basic cost vector, so the range of the change of CB is given by we'll see second cost change of second cost less equal to minus to be minus CJ ZZ. This is actually optimality conditions for any linear programming problem. This implies that actually del C2 minus 61 by 8. Actually this CJ minus ZZ we get in this table minus this minus 61 by 8. So minus 16 by 8, we get actually del C2 less equal to 61 by 8. And the variation of C2 will be C2 less equal to just adding the coefficient of the given simple linear programming problem. C2 equal, coefficient of C2 was actually minus 1, just adding minus 1 here, we get 53 by 8. So C2 is equal to 53. This is actually a condition for C2. Also for C1 and C3 are the basis vector. So the range of the change, discrete change of first cost vector is given by, this is actually formula for finding the cost vectors. So this is the maximum, and CJZJ, actually CJZJ are the actually minus 61 by 8, minus 1 by 8, and minus 13 by 8. How we get actually this? Actually get it from this is the Cj minus 13 by 8, minus 1 by 8, and minus 61 by 8. This is the actually coefficient of z, and this divided by, actually we get 5 minus 61 by 8, 5 by 4, and this 1z, the y z1. So yz will be the coefficient of actually 5 by 4, 1 by 4, 1 by 4. This is the 5 by 4, and this is the 1 by 4, and this is the 1 by 4. That means first row of the first basic variable, decision variable. So this divided by this divided by minus 1 by 8 divided by 1 by 4, 3 by 8 divided by 1 by 4. So we get actually this one. So this is equal to change of in variation del C1 is equal to, actually there is no values which is less than 0 in the first row. So again we observe here there is no value in the negative values. This is why no decision variable is negative in the first row. So we did not get the any value yz1 less than 0. This way, this is the maximum values, minus 61 by 10, minus 1 by 2, and minus, this maximum value is the actually minus half. So minus half less equal to del C1. Hence, the variations of first cost vector is minus half plus this is the given coefficient of our first cost vector 2. In the objective function, the first cost vector was C1 equals to what was 2. This is why just changing minus half plus 2. This is the effect of first cost vector. Also the range of third cost vector, similar formula we get maximum, and this is the value minus 16 by 8 and minus 13 by 8 in the third column. Actually in the third column. This is the third column, minus 11 by 8, this divided by this divided by this, and this divided by this is the positive values for third row, the positive values, and this will be the maximum, and this is the negative values for the minimum. This is why minus 61 by 8, 11 by 8, this is the positive value, minus 13 by 8. Variation of third cost vector less equal to minimum negative values, because y3 z3 less than 0. So for this value we get only minus 1 by 8 divided by coefficient of objective function. So in this way we get the variation is actually third cost vector variation, this that is minus 13 by 3 less equal to change in third cost vector less equal to 1. So the variation of third cost vector will be, actually 3 is the coefficient of our given third cost vector in the objective function. So in the objective function, actually third cost vector what was? Actually we get third cost vector. This is the first cost vector 2, and second cost vector C1, C2 equals to minus 1, and third cost vector C3 equals to 3. This is why we are adding here 3. So this is why we are 3 minus this. That means adding the given third cost values on both sides. So we get the limit minus 4 by 3 less equal to third cost vector less equal to 4. This is actually our required second cost vector and third cost vector in the discrete changes of the sensitivity analysis. Now we will discuss the variations of requirement vector, third requirement vector B3. You must know the B inverse. B inverse actually which one? This one. Minus 1 by 4, 0, 1 by 4, minus 3 by 8, 1, minus 7 by 8, minus 1 by 8, 0, 3 by 8. This is the whole actually B inverse. Okay, inverse matrix. So and requirement vector you must know. So this is the B inverse, and the basic XB will be 7 by 2, 19 by 4, 9 by 4. So from where we get this 7 by 2, 19 by 4, 9 by 4. This is the actual was solution. So in the similar way, the range of the discrete changes of requirement vector, this is given by the formula this. So maximum x minus xbi divided by xbi3. 3 is for only third requirement vector, but if they are 1 then b1, if they are 2 then b2, in this way. So for positive third column, third row, we get minus 7 by 2 divided by 1 by 4. Actually this one, this is the 7 by 2 xbi and divided by coefficient of third column. So similarly, this is the another one, 9 by 4. This is the 3 by 8. This values negative. This is why it's fall in the minimum part. So 9 by 4 divided by 3 by 8. And in the minimum part, 19 by 4 divided by minus 7 by 8. In this way, we get the another inequality for requirement third requirement vectors. So in this way, the minus 6 less equal to a change in the third requirement vector less equal to 38. So the variations of B3 is actually B3 was in our given problem, B3 equals to 8. So adding 8 on both sides. That means in our required, in our given problem, B3 equals to 8. This is why we are adding here 8 on both sides. So we get the actually requirements, variations of third requirement vectors. So thanks to everybody.